So we work in the infinite square world. And you remember the geometry. The geometry was that if we are having on this axis x and on this axis the potential, which is a function of x, and here it is 0, and we are having here a, then the walls are having infinite potential, while in between these walls means it's a square potential. So in this region the potential is 0 and the particle is moving under no force, right? Means particle is free to move in this range. So we are having our equation that v of x is equal to 0 if x is between 0 and a, and this potential is infinity elsewhere. And further, you remember that we started with the Schrödinger wave equation, which was I h bar curly sine x of t by curly t is equal to minus h bar square over 2m curly square sine over curly x square, this is also xt, plus v of x and sine xt. We solved this equation, and then you remember that for big psi x of t, we wrote that it will be the sum of x0, means the time independent wave function, and e to the power minus I e t over h bar. When we solved this equation, then we came out with the means when we solved for psi of x0, then for this system we found that psi of x0 means now not to write 0 because it is time independent, so I am writing psi x, and this is equal to 2 over a and sine of n pi over a x. So is when n will change here, then I will have another wave function here. So I write the subscript n with this as well. And this is the solution of the time independent Schrödinger wave equation, and we call this one that this is representing the different wave functions, the different states of the particles in this system. And we plotted them as well in the previous lecture, and the energy associated with this state is En equals n squared pi square h bar square over 2m a squared. And the energy came out to be the integral multiple of this. Here and here, n is equal to 1, 2, 3, and so on. You remember that we didn't include n equal to 0 for reasons which were against our geometry. So now these wave functions are these states of our particles are having some exceptional properties. What are those exceptional properties? We will have to discuss one by one here. If I put sine 1 of x, because n can be 1, 2, 3, then I'm having 2 over a and sine pi x over a, because n will be equal to 1. And you remember that how we plotted this thing, that when x will be equal to 0, we are having this wave function 0. And when x was equal to a, again this wave function was equal to 0. And when x was when x was a by 2, then we were having pi by 2 and it was maximum. So its shape was like this, that it starts from here and ends up here if this is point A. And this is A by 2. If I write sine 2 of x, then it is 2 over A and sine, so n will become equal to 2. So it is 2 pi x over A. And about this one, we came to know that this one is somehow, when this is A, means the same position A, and this is 0, the same position. Now here, when x is equal to A, then sine 2 pi is equal to 0. And when x is equal to 0, sine 0 is 0. So at the 2 points here and here, we are having this wave function equal to 0, just like this one. But when x is equal to a by 2, means the midpoint of it, then I have sine pi, and this is again 0. So, and if I check this one on a by 4, then I am having the maximum of this one. On this side as well as on this side. We have plotted these in detail in the previous lecture. I am now summarizing them. So what we get something like this. So one node, you can say one 0 point has been increased. Means our wave function is now such that it is crossing the 0 point and then returns to its original position. And similarly, we calculated psi 3 of x, and then it was 2 over a, and sine, then this will be 3 pi x over a. And we came to know for this that one cycle will be included with this one, but from 0 to a. Means instead of 2 cycles, we will have now in this range 3 cycles. 3 shapes, not cycles, because cycle is complete, you can say this rotation. We will have one crest, one trough, and then another crest. So if I look at this one, then such a wave function, such a state I call an even wave function, an even, can say shape. This one is having odd side with this one, and then again so on. So it is like even and odd combinations. A particle cannot exist at any point according to its wish. No. It will either exist at one level or the other level. In between, its probability will go to 0. There are few things here. the probability of this particle on the walls is equal to 0. This was understood earlier when we were just, you can say, considering the situation. But in this geometry, by doing our mathematics, we came to know that there are certain points for a certain level where the probability will also be 0. The particle will not exist at a certain point in a certain state. And now we actually study some properties of these states. That what are these states? So the very first one, that the set of psi n's of x has the following properties. Has the following properties. Now, what are those properties? One we have explored, and it is this one, that they are alternatively even and odd functions. They are alternatively even and odd, because we got even, odd, and so on. The next is, as we go up in the energy, means as the energy increases, means from one level to another level to another level, then the nodes increase. You see, here were two nodes, the beginning and the ending, and here are three. Means the wave function is passing to 3 0 positions. If I add another one, then one node will be added more. So as we go up in energy, means this one is level 1, this is level 2 and level 3 and so on. So as we go up in energy in this potential well, then the nodes increase. And the very important one of this one is that they are mutually orthogonal. Means the one wave function is perpendicular to the other wave function. And if I take, for example, sine with m of x, m is a number 1, 2, 3, and sine n of x, n is also a number 1, 2, 3. So m is one sequence, n is the other sequence, and if I do integrate them, and from this one I can write, mean the general condition is from minus infinity to plus infinity. Here in our geometry it will be from 0 to a. So I am not writing any condition on it, but it is generalized. Psi m, psi n. Now you know two wave functions you cannot multiply like this, but you will have to take the conjugate of one and multiply it with the non-conjugate. And if this thing is equal to 0, what does it mean? It means one function is even and the other function is odd. Like if you are having two functions mathematically, f of x and g of x, and this is a even function and this is odd function, or this is even and this is odd function, then this thing will be equal to 0. Right? So this condition is holding here. because we are also having odd and even states. So this will come out to be equal to 0, right? And when this is equal to 0, then you can have the condition that if m is not equal to n, then it will be equal to 0. If m will be equal to n, then if m will be, you see, if this one is different and this one is different, then it will be equal to 0. If this one and this one are the same, means they are the same wave functions, then their magnitude should come out to be equal to 1 if m is equal to n. When this will come out to be equal to 1? When your wave functions will be normalized. Because for normalized wave function, when m and n will be equal to the same, then this, for example, this is psi n conjugate psi n, then it will become psi n mod square. And psi n mod square for a normalized wave function will be equal to 1. And this will hold this condition. These two I can write in a combined form. You know about the Schrödinger delta. Psi m conjugate of x psi n conjugate of x dx is equal to Schrödinger delta mn. You know about the Schrödinger delta. Schrödinger delta is that this is equal, this will be equal to 0 if m will not be equal to n, and this will be equal to 1